Hello everyone. So let's talk about digital signatures. We're going to talk about two digital signatures today. So um, the scenario is Alice wants to sign a document and send it to Bob, her financial officer. Okay, wants to sign a message. Let's call it M. Okay, and send it to Bob. Wants to send it to Bob. Get my pencil a little bit heavier. Okay, so M is what she wants to send it. So this message M could say anything. It says, please deposit, I don't know, $1 million to Dr. Afra. So that's the message she wants to sign and send it to Bob. So Bob is her financial officer. Okay, so this is what she does. Okay, I'll show you what she does first, and I'll show you what he's gonna do. This is an RSA type signature scheme, and the next one that I'll talk about will be an ElGamal signature scheme. So this is RSA signature scheme. So first she chooses two large primes. These are two large primes, and computes n, p times q, and phi of n, which is p minus 1 times q minus 1. Okay, she keeps the phi of n secret. She's going to make n public. Okay, so that's the second step. Sorry. Third, she selects an exponent. She selects an exponent e such that e and phi of n are relatively prime. Okay, so GCD of e and phi of n equals 1. So e has an inverse mode phi of n. And she's going to compute d, the inverse of e, mod phi of n. So mod p minus 1 times q minus 1. Now she's going to publish n and e, the exponent, the public exponent, and the number n. So that's just out for public, so everybody can see that. Okay, now to sign the message M, this is what she's going to do. Okay, to sign M, she computes y, which is equal to m to the power of d mod n. So d is not public. Nobody knows d. Everybody knows e and n. And I need to lose a number. 1, 2, 3, 4, 5, 6. Okay. On my note, I lost a number. So she sends the message in the clear and y to Bob. So what does Bob do? So on his side, Bob wants to verify that she signed it so he can transfer the money. Okay? Bob has to find out that she signed the document. Okay, so, and Bob has this pair information. Okay, so he can calculate, downloads. So step 0 is downloads E and N, and he downloads the message. He has Y, M and Y. Okay, and now he computes Z, which is Y to the power of E mod N. Okay, so he compares Z and M. So if Z is M mod N, then the signature is verified. So the message is M. The signature part is kind of like the Y. And so is Y really the correct signature? Does this verification work? Let's check, okay? So Z, he wants to calculate Z as y to the power of E mod N. But we know that Y is calculated as M to the power of D mod N. So we're going to replace M to the power of D for Y. So this is M to the power of D to the power of E mod N. This is actually M to the power of D times E mod N. Well, D times E is D and E are inverses mod phi of N. So this is kind of like M to the power of 1 plus some constant multiple of phi of N. So, but M to the power of phi of N is 1. So this is 1. 1 to the power of K is 1. M to the power of 1 is M. So this is not M prime, this is M to the power of 1. And that gives you M. So that's just what he's trying to do here. He checks that Z is actually M. What is Z? Z is Y to the power of E. So he simply calculates Y to the power of E. And if that's equal to M, then the signature is verified. He's going to do the transfer because he's sure that she signed it. Now, let's see if we can forge the signature. Okay? To forge the signature, what does Eve do? Well, she might put a different message. So let's see if she can forge the signature, okay? So Eve writes a message M2, which could say deposit $1 million to Eve's account. And she's gonna send M2 and Y to Bob, impersonating Alice. So he calculates Z2, which is Y to the power of Y to the power of E mod N. Well, the Y to the power of E mod N gives him M. So this is not the same as M2. So he sees M2 and he calculates Y to the power of N, y to the power of m, it's not the same as m2. So he doesn't believe. So since m is not the same as m2, Bob puts Eve to jail. Well, doesn't deposit the money. Now, suppose she wants to forge Alice's signature different way. Okay, so suppose she has the message M2 and wants to get Y2 such that Y2 to the power of E is equal to M2. So she can send M2 Y2 to Bob. So if Bob gets this as if it was sent from Alice, he's going to believe the message and then does what the message tells him to do. However, finding Y2 is like so solving Y2 to the power of E is equal to M2 mod N for Y2 is called a discrete log problem. This is proven to be as difficult as factoring P and Q. So this is not solvable as non-solvable as factoring P and Q. If we can factor P and Q, we could do everything, but P times Q. So factoring P times Q is difficult, and that's as difficult as solving this equation for Y2. We know this, but we don't know Y2. And this is difficult to solve. So this is what we call RSA signature scheme. So the next one that I like to talk about is what we call ElGamal signature scheme. Okay. The first one, the RSA, is, the calculation is similar to the public key crypto system that we learned about RSA. This one also has something similar. We didn't talk about this, so I'm going to start from scratch on this one. So again, the same scenario. Alice wants to sign the message. The message is not secret. That's not the problem. We don't hide the message. What we're sending is the message is now signed by Eve, sent to Bob. So that's what the idea is. Even in the previous example we saw, the message is not hidden. We're not encrypting the message. Okay, so she's gonna choose. She's gonna do this. She's gonna choose a large prime P and a primitive root alpha mod P. Okay, what that means is alpha to the power of 1, alpha to the power of 2, up to alpha to the power of P minus 1 make not in the same sequence, but this makes the numbers 1, 2, up to P minus 1. So alpha to the P minus 1 being 1. Okay, so the first time you get 1 when you raise alpha by any constant is at p minus 1. So that's why we call this a primitive root mod p. We talked about this in class. Okay, so these in not in the same sequence but in different sequence is equal to that set. Okay, so alpha to the power of p minus 1 is 1 mod p, and that's the first time alpha to the power of 1, alpha to the power of 2, alpha to the power of p minus 1 is the set 1, 2, up to p minus 1. Okay, so that's the first time that we get 1 by raising alpha. P minus 1 is the first one. It's the first time we're going to get p minus 1. And next she chooses a number a between 1 and p minus 2. So an exponent a between 1 and p minus 2, and keeps it secret. Okay, okay, so she keeps it secret, and she computes alpha to the power of a mod p. Okay, so to recap, what do we have? What we have here is p is a large prime, alpha is a primitive root mod p, a is simply a constant between 1 and p minus 1, and beta, which is a to the power of alpha, no, alpha to the power of a mod p. So we have these 4 values, and she publishes, so back to Alice, she publishes these 3 numbers, p, alpha, and beta. Okay, so these are public, so anyone can see them. Eve can see them, or Bob can see them. So Bob will download these to verify the signature. Okay, so these are public. The only thing private is the number a. So p, alpha, and beta are public. Okay, so a is private, so this is secret. Okay, now to do the signature, the message M, she selects a constant, a secret constant k. Okay, such that the GCD of k and p minus 1 is 1. We want the k to be relatively prime to p minus 1. I will tell you why later on, but k has to change every time the message changes. Okay, for every new signature, every new message, she has to pick a different k. But alpha, a, and p can be kept constant. Okay, so if k is out, everyone can can forge her signature. So k is, or I mean, if she repeats the same k for 2 different messages, then it's as simple as solving a congruence equation. All right, so k is picked, and now she's going to compute r, which is alpha to the power of k mod p. So r now is between 1 and p minus 1, because it's mod p. Okay, so r is a number between 1 and p minus 1, but r is calculated as alpha to the power of k. And now, and also she computes S, which is K inverse. So K is relatively prime to P minus 1. So it has an inverse, mod P minus 1. So the message is here, A times R. Okay, so multiply A and R, subtract it of M, multiply it by K inverse. This time do the calculation mod P minus 1. Do the calculation mod P minus 1. Not mod P, but mod P minus 1. Now the signed message is the message M, the value R, and the value S. So she sends it to Bob. Okay, so Bob gets these 3 numbers. Okay, so how does he verify this message? Once again, R is calculated as alpha to the power of K, and S is calculated as just this linear multiplication of K inverse times M minus AR, mod P minus 1. This is calculated mod P minus 1. Okay, this one is calculated mod P, but next one is calculated mod P minus 1. So that's what she's sending to Bob. So what does Bob have? Bob has these 3 values, the message and the signature parts, and Bob has these 3 values. Bob has P, alpha, and beta. These 3 values, everybody has them actually. Okay, everybody has them, even Eve can see them. So the verification process goes like so. Okay, so Bob, first step is downloads, what was it, P, alpha, and beta. Also M, R, and S already sent to him. Okay, he also has M, R, and S. And now he computes V1, which is equal to beta to the power of R times R to the power of S mod P. Okay, he has beta that he downloaded. He has R from the signature, and he has S from signature. These are the 3 numbers he needs, and P also. So he calculates V1 beta to the power of R times R to the power of S mod P. And he computes another number V2, which equals alpha to the power of M mod P. Okay, so these are the 2 values he computes and compares V1 and V2. Okay, compares V1 and V2. So signature is verified. If V1 equals V2 mod P. If these 2 are equal, then the signature is verified. Otherwise, he rejects the signature. Okay, otherwise he rejects the signature. So let's see how the signature verification process is valid. I'll show you how that is valid, and then I'll stop the video. We'll talk more about it, how this works in practice. In practice, we don't sign M, we sign the hash values of M. So that's the signature scheme. We hash M, and then we sign it, and then send M and the hash values in the signature. Yeah, and then I'll show you how that birthday attack can be applied to forge a signature if Fred, the accountant, wants to forge it. And so we talked about this in class, but we'll start with that. So I'll just do the verification now. Okay, so what we have v1 equals b to the power of r times r to the power of s, and v2 is alpha to the power of m. Why should these two be equal? I'm going to start from v1 and walk myself towards alpha to the power of m and get v2. Okay, all right, let's see. Let me change pencil. So v1 was beta to the power of r times r to the power of s mod p. Beta was a to the power, alpha to the power of a. So that's the power of r. And s was, let's check, what was s? S was k inverse times m times minus ar. Okay, so I'm going to stick that in for r, for s. K inverse m minus ar. Okay, this is mod p minus 1. So this is equal to a to the power of alpha to the power of ar times r was alpha to the power of k. Okay, times k inverse m minus ar. Okay, well, this is equal to alpha to the power of ar times alpha to the power of k inverse. This is mod p minus 1. The exponents work mod p minus 1. Okay, and k times k inverse mod p minus 1 is 1 mod p minus 1. That's phi of p. Okay, so this is giving you alpha to the power of ar times alpha to the power of m minus ar mod p minus 1 in the exponent. So this is the same as alpha to the power of m minus ar plus ar. Or I think I put it the wrong order. Ar plus m minus ar. And this gives you alpha to the power of m mod p, which is actually what v2 is. This is what v2 is. So the signature is verified. Okay, so if Eve wants to forge and sends her message along with this pair of signatures, none of these calculations would work. Okay, her new message, alpha to the power of the new message, will be a different v value. It's not going to match with v1. Okay, so if she sends a new message with the same r and s. And the other thing that we will look at when we come back from the break is what happens if Eve picks the same k for two different messages and two different signatures. Okay, the same p, the same alpha, the same now the same k. Well, if she does that, then she should be in trouble. We'll talk about that later. And well, this is it. And have a nice break. We'll do a little bit more when we come back. Thank you, and I'll see you on Monday after the break.